Hi. So the video here is looking at a vector solution to the following problem. And the problem is we want to show that the sum of the squares of the lengths of the diagonals of a parallelogram is equal to the sum of the squares of the lengths of the sides. So we're given a shape that's a parallelogram, and below that's our shape ABCD. And we're trying to find the sum of the squares of the lengths. Now, when we're looking at vectors, the length is going to be magnitude. So we're wanting to get a magnitude of the sum of the squares of those lengths. So we're going to come up with a formula for that in a moment. And we're going to show that, hopefully, when we work that through, that's going to be equal to the sum of the squares of the lengths of the sides. So our diagonals in this parallelogram are AC and BD. And our sides are obviously AD, DC, BC, and AB. I'm using them in the direction that my arrows are shown. So first up, what I'm going to do is come up with another way of writing our diagonal. So our diagonal AC, from A up to C here, is going to be equal to AD plus DC, but it's also going to be equal to AB plus BC. Just change that to be BC up there. So our diagonal AC we're going to use as AB plus BC. Now, because it's a parallelogram, just remember that the opposite sides are equal. So the side AB and the side DC are actually equal. So the vector U applies to both of those, and likewise for vector V. So with our other diagonal BD, we've got two ways of writing that. We can write that as vector BC, take away vector AB, which is what I would prefer, well, was what we need, not what I would prefer, but we need it to be in that format because we want to have the same letters as AB. But you likewise could have written the vector BD in terms of the other sides as well. So you could have used your AD and your AB. But I've written them like this because we want to find a way of working forward for those. Let's put that information into our proof. So our proof is saying, well, we want to show that the sum of the squares of the lengths of the diagonals. Well, the lengths of the diagonals are magnitude. So the lengths of the diagonals are AC and BD. But because we want to connect everything together, I could write that as the other solutions I've got up here. But we want the sum of the squares of the lengths of the diagonals. So we're going to sum them together, but we want the length and we want to square it. So we're going to have the sum of the squares of the lengths. So we're going to have for AC, AB plus BC, noting these are all vectors. So that's the square of AC. The square of the length of AC is this one here. Okay. And now we're going to do the square of the length of BD. So that's BC minus, oops, my pen's not good here, AB. So here is the sum. There's our sum of the squares. There's our squares of the lengths of our diagonals. So we've got that first part. And now let's expand that and see if we can get that to work through to be equal to the sum of the squares of the lengths of the sides. Now, I just want to make a little note over here that when we had two vectors that were the same and we did the dot product of those two vectors, that was equal to the magnitude of that vector squared. And we're used to going this way. But what we actually have over here is the magnitude of our vectors squared. So we can actually write that and take that apart as the dot product of the two vectors that are inside there. So how we could write this now is the dot product of AB plus BC dotted with AB plus BC plus the dot product of the next two as well. So BC minus AB dot product BC minus AB, noting they're all vectors. and this dot is the dot product. So we can expand that out. Okay, so I'm going to pause the video and expand it out and show you what I end up with. So if you want to have a go at expanding that and check with what I've got, that would be a good idea. So I've just color coded the expansion so you can see what I've gotten. So these two here, we've got ab.ab. So I've got two lots of ab.bc and bc.bc. And the same with our purple ones. Okay, two BCs dotted together, two ABs dotted together. But we've got minus two lots of this. So I'm going to join those middle terms together. And what we're also going to note is when we have the dot product of two things that are the same, remember our note over here? I'm going to write that as the magnitude of that square. So we'll have the magnitude of AB squared plus two lots of AB dotted with BC plus the magnitude of BC squared. That's the yellow stuff done. Plus, let's do the purple ones, the magnitude of BC squared minus two lots of AB dotted with BC plus the magnitude of AB squared. Okay, so if we neaten that up one step further, we can cancel out this 2 and this minus 2 over here. So what we have actually is two lots of vector AB, or magnitude of vector AB squared, plus two lots of the magnitude of vector BC squared. Now we've basically finished that proof now. We just have to go back and note one last little thing. Back in our original diagram, if we think of what we actually had, we had a parallelogram. So by definition of a parallelogram, the opposite sides are equal in length, which we talked about. So what we can say is that the magnitude of AB is equal to the magnitude of DC, so they're opposite. And we also know, and I should put little vector arrows up there, and the magnitude of AD is equal to the magnitude of BC. So noting that, what we could actually do is go down here to our solution, and we've got basically two lots of AB squareds and two lots of BC squareds. So I could write that as AB squared, back to how I had it before, basically, AB squared plus AB squared plus BC squared plus BC squared, noting that BC is the same as AD and DC is the same as AB. So I've got DC and a BC. So that's, oops, my pen's having problems. Magnitude of AB squared plus the magnitude of DC squared plus the magnitude of BC squared. Oh, and I forgot the name of the last one. What's the magnitude of our last one? The last one's AD, which is what we were trying to prove to start with, is the sum of the squares of the lengths of the sides. Write that in there. So we've finished our proof. So we've gone from working out the sum of the squares of the lengths of the diagonals, and we've moved all through our proof, and we've shown that that is equal to the sum of the squares of the lengths of the sides. The end.